Hello, everyone. Welcome to the workshop on graphs and data science, where we'll discuss their applications to optimization and beyond. So as a quick overview of today's workshop, we will first begin by motivating optimization. We will then motivate graphs in the context of data science, and we'll move on to a quick demo to show you how to use the NetworkX package for Python. Next, we'll discuss several optimization algorithms, and we'll move on to a demo using the USCA 312 dataset, which is a dataset of 312 cities across North America and the distances between them. After that, I'll suggest some references and further reading. My name is Tom. I'm a second year studying computer science at the University of Waterloo. And let's begin with motivating optimization. So in data science, often in machine learning problems, we often need to minimize or maximize some function. We typically refer to it as the cost function. And our task is to find the value for which it's at a minimum. Thus, this idea of optimization is very, very prominent in machine learning. Hence, understanding optimization will allow us to approach machine learning problems a lot more effectively. So now, in particular, let's take a look at functions of a single variable and how we might be able to optimize these to find their minimum. So here on the left, we can see a function that is convex on any interval. So that means we can pick any interval at all, and the function will be convex. In contrast, the function on the right is convex only on some intervals. Now, with the case of the left function, locally optimal decisions in the sense of going downhill, you can think of it that way, or using the idea of gradient descent. So looking at the gradient of the function and going against it will always yield the optimal solution. In other words, we can take a locally optimal decision, and that will lead to a globally optimal solution. On the other hand, we often deal with functions that are convex only on some intervals. And so a greedy approach might not yield the optimal solution. In other words, it might yield a suboptimal solution. In particular, if we begin our gradient descent over here, we may end up in this local minimum, and we will not be able to descend down any further without going uphill. And so a greedy algorithm will not find this global minimum, which has a much lower cost. Now, to motivate a little bit of graph theory, it is really the mathematics of relationships. So you can think of calculus as mathematics of change, probability as mathematics of chance. Graph theory is really studying the way that objects may relate to each other. Now, in graph theory, we have several fundamental objects. So we have vertices, or otherwise known as nodes. So you can see on the right, the black circles represent vertices or nodes. And now the links between them are edges. And the links between them could represent a variety of different things. So you could think of vertices as cities, and the links are the roads between cities. Or you can think about the vertices as being people, and a link between two people representing that they know each other. And now a graph then is just a pair of two sets, some nodes and some edges, like you can see on the right. So the graph at the top is an example of an undirected graph, where the edges they sort of go both ways. In contrast, the graph at the bottom is a directed graph, where the edges point in one of the directions. You can think about the edges in the illustration at the bottom as one-way roads. So you can go one way and not the other. Now, here are some examples of graphs that are prominent in data science. So perhaps one of the most prominent appearances of graphs in data science is the neural networks, which are in essence computational graphs. So over here on the left, we can see a neural network with multiple layers. Another major application of graphs is currently graph databases. So Neo4j is an important example of that. Now we are going to move on to a little demo using the NetworkX package in Python, which allows us to manipulate graphs very easily. And that will allow us to build some intuition for working with graphs. Right? Import the package, create the empty graph. Now, continuing on, we're going to add a node to our graph, and we do so by calling the function add node. So right here, we have added the string u, consisting of a single character u, to our graph. Now we're going to do some visualization. And at the moment, don't worry too much about the imports at the top. We will take a look at a few more examples of visualizations in a little bit. So now let us quickly call the method nx.draw of our function of our graph G, and we can see that we just get a single node. Of course, when we move on to larger data sets, it is simply impractical to be adding nodes one by one like we did here. So we can also add nodes from any iterable container, such as a list, as you can see over here. So I've just added WDS to our graph. So now we have UWDS. Let's visualize the graph now, and we can see some more nodes. So now we've got 4. Similarly to just adding plain nodes, we can also store attributes with every node. So for instance, maybe the different nodes, they might represent items in some sort of a store. So you might want to store a cost as an attribute. I will be, yes, indeed, just to answer the question in the chat, I will be sharing the notebook after the presentation, so you will have that available.
Okay.
And so here we add nodes from here, again, an iterable container, a list, and every item is a tuple containing the node itself and a dictionary of attributes. So in this case, cost. If we want to see the nodes at any point, we can simply call g.nodes, and here I'm simply converting it to a list because the object that it returns is specific to NetworkX. It's a node view object. Typically, you just want to convert it to a list. And we can similarly retrieve the attributes. So let's retrieve the attributes of the node M. So I've added ML over here. If we wanted to retrieve the letter M, I can see it has retrieved its attribute. Now, adding edges is very, very similar. Right here, I've just added an edge from M to L. And so our graph now contains the edge from M to L. You'll see it once we visualize it in a little bit. Now, sometimes you may try to add an edge and the nodes are not yet present in the graph. So if you recall, our graph right now only contains UWDS and ML. If we try to add A to it, the vertex isn't currently in the graph. So if we try to add an edge from U to A, we actually end up adding the node A to the graph as well, which is done for us by this built-in function. Let's visualize the graph now. And we can see our graph now, it looks like so, with a couple of edges, right? One between A and U, and one between L and M. Now let's add some more edges and visualize our graph. I've just added some more edges and called the draw method, and this is what our graph looks like now. And when you saw us retrieve the attributes of a particular node, if you're storing attributes with edges, you may also retrieve them at any point using the square brackets operator, like so. Now, sometimes we need a somewhat of a different representation of a graph. In particular, in many, many problems, we want to know the neighbors of a particular vertex. In other words, the adjacency list of a particular vertex. So all the neighbors of a particular vertex. Here, let's take the vertex W. We see that S, M, and A are adjacent to W. So the adjacency list of W would consist of those 3 vertices. Let us find the adjacent vertices to A, and you can see it's these 4 nodes, and you can also see them in the plot at the top. Now, the degree of a vertex is another very, very useful property. In particular, it's in a directed graph, it's the number of edges that a node has. So the degree of W in this case would be 1, 2, 3, because it has 3 edges. And if you may notice, this graph is undirected. For a directed graph, we can also define the in degree of node. So that's all the edges incoming into that node, and the out degree, that's all the outgoing edges. So let's retrieve the degree of U and also the degree of W. You can see that the degree of U is 1 and the degree of W is 3, also evident from the graph. Similarly, we can access edges, give them attributes. So here ML time gets the attributes of now. So if we try to retrieve ML time, we see that it is right now. That is the basic workings of graphs and how you would typically utilize them. Now let's take a look at a few visualization examples. And all of the examples that are listed below are from the NetworkX gallery, which is, by the way, referenced as well if you would like to see more of these examples. Now, in most cases, it isn't particularly necessary that we visualize the graph, but it is fairly interesting. And most of these plots are very, very exciting. So all of these are specific kinds of graphs that are that have been provided in the documentation, and you can visualize them as follows. Typically, you provide a set of attributes like specific node lists that you want to visualize. You may give it a color map, and so you may get very, very interesting plots. We'll do an example in a little bit when we go to visualize our other data set, which is the data set of 312 cities and the distances between them across North America. So let's go back to the presentation. So where do graph theory and optimization meet? They actually meet in a lot of different areas. And one of the prime examples of an optimization problem in graph theory is the traveling salesman problem, which is very great for providing some intuition into sort of the workings of optimization and also graph theory. So formally, according to Encyclopedia Britannica, the problem statement is as follows. The nodes, cities of a graph are connected by directed edges, routes, where the weight of an edge indicates the distance between two cities. The problem is to find a path that visits each city once, returns to the starting city, and minimizes the distance traveled. So in other words, we're given a bunch of cities, some distances between them, and we want to start a particular city, visit all other cities, and return back to our original city. Now, the specific kind of graph that we are talking about here is a complete graph. So you can see an example of a complete graph on the right. This is a complete graph with 8 edges, sometimes denoted as K8. It basically means that for any 2 vertices in the graph, there is always an edge between them. So you can pick any 2, like these 2, for instance, and there is an edge between them. So this is an example of a complete graph. And whenever we're dealing with a traveling salesman problem, we typically are interested in the case of the complete graph. So we can, from any city, we can travel to any other city. And the edges between the cities represent the routes, and the weights of those edges represents the distances between the cities. So what approaches can we take? There are several, and at this point, we're starting to get into several optimization algorithms that we're going to discuss. In order for us to use them a little bit more effectively, let's define some terminology. So let's define a state as a path. So just a sequence of nodes. So you can think about a graph and you're traveling through every city and you're visiting every city exactly once. So that's our state. Every state will have an energy. That's the length of the path. So you just add up the distances of every edge, and that will give us the energy of that state. Now, in order to generate a new path, we will just simply swap a pair of nodes in our state to generate a new sequence of nodes. And that's how we're going to generate neighbors of a particular state. What approaches can we take to actually solve the problem? Well, you can think about the idea of gradient descent. Well, suppose that this little plot on the right gives you the cost for various states. So let's suppose we start over here, and the adjacent states that we can achieve by swapping two nodes are to the left and to the right. What gradient descent says is we will only take the switch if the energy of the new state is lower. So say we start right here and we take some more switches and we switch to the neighboring state and we end up in this local minimum, which is of course far from the global minimum, which is over here. And so gradient descent might lead to a suboptimal solution here. On the other hand, we can take the approach of a random walk. So whenever we generate a new state, always take the switch, regardless of the energy difference. So even if the new state's energy is way higher than the energy of the current state, we will take the switch regardless. Now you can you can sort of start to see that this might not lead to an optimal solution at the end, but it seems to overcome the problem of getting stuck in this local minimum. The approach that combines the two is the method of simulated annealing. It's called that way because it's similar to cooling of a metal. We basically begin in a state of a random walk. So in the very, very beginning of our algorithm, we're performing our moves at random. We're performing a random walk. But over time, as the temperature decreases, we're going to transition into more of a gradient descent. So at the very beginning, our decisions are similar to this idea of a random walk. And the cooler the temperature gets, the further we are into the algorithm, the more it resembles gradient descent. In other words, we can put this in terms of the following: the probability of accepting a more optimal state increases over time. On the right, you can see a little bit of code. This is pseudocode written by Nathan Roy, and it gives a very good insight into how the algorithm works. We begin by initializing our state with any state at all, and then we proceed to our main optimization loop. T-current in this case would represent temperature. While our current temperature is greater than some minimum temperature, we will generate a new number, a new neighbor, and store that in our new state. And now, if the probability of the current of taking the switch, given the energy of our current state and the energy of our new state, as our temperature is greater than some random number between 0 and 1, we will take the switch. And now if we arrive at a case that's actually better than the state that we've seen, we will memorize it so that say at the very end we end up at a state that's a little bit less optimal than the best state that we have ever found. This allows us to memorize that state. And then we'll update our temperature. And the way we can sort of simulate the passing of time is with any decreasing function we'll do. So you can literally decrease temperature by 1 with every iteration of this loop. Now, other functions can be used as well. You can also get even closer to this idea of simulated annealing and cooling of a metal with a decreasing exponential function, which simulates Newton's law of cooling. So the temperature will be decreasing in accordance to that. But in practice, any decreasing function works just fine. So at the very end, we can output the results. And now let's take a look at the demo and start working with the data set. So again, we begin by importing our packages. In this case, we don't need much other than the NetworkX package itself and NumPy, the computational library for Python. We will load the dataset, and the dataset is referenced in the PowerPoint, so you will have access to it. The text file has been slightly modified to facilitate this input entry over here. So we've just read in a text file, and currently we can see that its shape is 97,344 by 1. So right now it's an array, and according to the documentation of the data set, this distance file represents an adjacency matrix. So an adjacency matrix is a matrix in which the jth entry represents the distance from the ith node to the jth node, or the weight of the edge from the ith node to the jth node. So since this data set contains 312 cities or 312 nodes, we will reshape it into that shape. And so, like I said, the ith entry will represent distance from city I to city J. This distance is in miles. It's just a small technical detail computed from the latitude, longitude data and rounded to integers. Now, this here is an adjacency matrix. And fortunately, NetworkX also has a method to create a graph from such a matrix. So we simply call from NumPy matrix on our data set, and we have just initialized a graph. We've loaded in the data set, reshaped it into an adjacency matrix, created a graph from that matrix, and also imported the names of the cities, like I said previously, initializing their coordinates and visualizing them with a plot. We have also visualized our graph, and so it does resemble North America, and so that means that we're on the right track in terms of visualization. So now let us actually tackle the interesting part, the idea of optimizing and finding the optimal path that visits every node in this graph, otherwise known as the traveling salesman problem. So some of the approximations that we're going to be using here are built-in functions into the NetworkX library, but they're only available in the developer preview version of the package. So if you would like to install that, you may execute these commands, but otherwise, there are other packages which I will also be discussing. So just importing the approximations for this particular instance of a traveling salesman problem, let us first discuss the approach of the greedy approach. In other words, the approach of hill descent or gradient descent. Whenever we swap a pair of nodes, we're going to take the switch only if the energy difference is lower. So running it, we can see that the cell has executed very, very quickly. And now if we compute the cost of this path, just calling some very idiomatic functions here, just taking the sum over the pairwise list of this path. So if you would like to see what the path looks like, it's some nodes starting at 0, going to node 96, and then 68 to 91, 15. What utils pairwise does is it will take that particular path and it will form another list where every other node is duplicated. So here from 0 to 96, from 96 to 98, allowing us to compute the total distance of that path as follows. So we arrive at the following cost for the greedy algorithm, 48,000 kilometers or miles. Now, as you can see, the greedy approach, or otherwise known as the approach of gradient descent, ran very, very quickly. And that is because it's a lot less computationally expensive than other approaches. For instance, simulated annealing. It can be mathematically shown that given enough time, it will yield the globally optimal solution. However, the downside is that it is very, very computationally expensive. So we are going to approach the traveling salesman problem using simulated annealing, and we are going to do so as follows. Setting our parameters in such a way that we can execute we can go through the entire algorithm fairly quickly. In practice, this simulated annealing approach, due to being a lot more computationally expensive, it would take much longer to run, even on modern computers. It could take several hours. So the specific package that we're going to use is this frigidum package, which implements simulated annealing in its most general sense. Now, by this point, you're probably noticing that this idea of a state and the idea of energy being so generic, not being specific to the traveling salesman problem, really allows this problem to be really allows for simulated annealing to be used in other contexts as well. All you have to do is define the objective function, which will basically return the cost of your state, and the state could be anything. It doesn't have to be a path for a graph. A transition function, which will basically yield a neighbor of your state. So here we've defined neighbor, which swaps two nodes two nodes in their path at random. And a random start function, which will initialize our algorithm to some random state. So right here, we are just basically initializing it to the graph, the vertices in order. So 0, 1, 2, 3, 4, 5, and so on. So converting the graph sheet into a list to get a list of nodes, and then getting the first node from that list and appending it onto this list. And here we are just making a copy of that list in order to not mutate the vertices over time as we perform our iterations. So let us execute this algorithm, and first executing that cell. We can see that the costs, at the moment, we have some minimum cost that we've already found. And for the current cost, you can see while our temperature is high, it's jumping up and down. So we are accepting less optimal states in the initial phases of the algorithm. While our system is still cooling down, we have high probabilities of accepting states that are not optimal. So our minimum remains the same, even though we've gone through a number of iterations by now. The specific parameters are just specific to the implementation of the package. So in practice, there is a lot of room for experimenting with the specific parameters that you're using for simulated annealing, which can also be seen as a downside, because for gradient descent, you can simply initialize it to a particular state and then swap neighboring nodes from there until you end up at a local minimum. Here, there's a lot more room for experimenting. And now, while this computation is running, I can answer any questions if anyone would like to ask a question. So over time, as our system cools down, we can see that we're no longer accepting states that are not optimal. So over time, you can clearly see that our minimum temperature and our current state is not changing very much, because we only really take the change if our new state is more optimal, in other words, has a lower cost. So as our temperature is cooling down, we have a lower probability of accepting a non-optimal state. And now the way that this workshop has explained simulated annealing is really meant to provide intuition and insight into the topic, and not as much of a mathematical and rigorous reasoning for why the methods of simulated annealing work. If you would like to read more, there are several resources referenced in further reading if you would like to find out some more about this topic. So here, as our temperature is cooling down, so it's very, very close to 0, while we started at 100,000. we are approaching the end of our algorithm. And as you can see, given the time of our workshop, we are not able to move past this very, very high minimum because, like I said, one of the downsides of simulated annealing is that it's very, very computationally expensive. Given enough time, it will arrive at a globally optimal solution. But as you can see, it is even on modern computers, it can take up a very long time. Now, to account for this, what we can do is use another approach, which is a lot more practical, which I'm going to demonstrate momentarily as soon as the cell finishes computing. In fact, we can terminate it and continue. So what is another approach that we can take? So with simulated annealing, the whole idea is escaping from a local minimum. So not being stuck at a local minimum, and so that we have a better chance of arriving at a globally optimal solution. Now we can sort of get close to that by initializing our greedy algorithm to a lot of different points. So initialize them to a wide range of states and run greedy algorithm from there. Now you can see that that's sort of similar to how simulated annealing would work out. In a sense, we are jumping all over the place, and then at the very end, we just pick the best solution that we found. Now, this solution might not be optimal, but in practice, it is likely to be very, very good. And of course, we don't explore every possible state because that would be equivalent to complete search, which is certainly impractical for a problem like this. When you think of 312 cities, there is certainly no way to perform a complete search over all of the possibilities because you're basically counting all of the possible paths. So what are all the possible ways you can arrange the 312 cities in a row and travel through all of them? 312 factorial ways. That's way outside of reason. So we have to use these optimization algorithms. So in particular, let us see what cost this new approach will yield by initializing greedy algorithm to a variety of different states. And now the easiest way of getting a new state is just to start our path from a different vertex. So this for loop will iterate through every possible city. So starting from the 0th city to city 312. And we will run our greedy algorithm from every node, starting at every node. And over time, we will simply pick the best cost that we find. So for every path that we find, we will compute its cost. And of course, initializing our best costs to a huge number, 1 billion, and then looking for a better cost over time. Now, here's the distribution of the costs that we come across by having our function initialized to different starting vertices. So here you can see that a lot of these starting points will result in a solution that's definitely far from optimal. So clearly better solutions exist than this solution at almost 53,000 miles. But we have also identified a solution that's significantly lower than any of the others. And so for practical purposes, this solution, even though it's not guaranteed to be fully optimal, we have a very, very good chance there's a good chance that in practice it will work just as well for our purposes. And now as an optional state, let's proceed to visualize the solution and actually see what it looks like and what nodes we have picked. Of course, this state, like I said, is not part of the, is not necessarily necessary, but it's a nice visualization. And here the figure size is 150 by 100. So this will, might take a while to generate. And so if I open this image in a new tab, which usually ends up freezing my entire browser. And so let's take a look at it. As soon as that loads, out of all the 312 vertices, we were able to pick, out of all the possible paths, we were able to pick a particular one. And so here, for visualization purposes, you can see the different cities and how out of all the 312 incident edges, we are only picking two, one to go into that city and one to leave that city. So here is another look at all the cities. So that concludes the demonstration of the NetworkX package and a quick little contrast between the various algorithms. It is important to keep in mind that while we have applied our algorithms to this specific instance of a traveling salesman problem, to this very specific data set, the functions could be anything and the states could be anything. That was the main idea behind all of this abstraction with having a state and giving every state some energy. So this very same method can be applied to a variety of different contexts. So now going back to the slides, some references that were used throughout. Of course, all of this will be made available if you would like to read more about them. But in particular, I would like to recommend the article by Nathan Roy, which goes into simulated annealing in a couple of more details and implements it from scratch. Moreover, there has been a rather recent publication titled Simulated Annealing Algorithm for Deep Learning, where this exact algorithm of simulated annealing has been applied to a convolution neural network on the MNIST dataset, so the dataset of handwritten digits. So this is a very interesting piece of reading in terms of that. And that concludes the content of this workshop. And if you would like to ask any questions, please feel free to ask them now. While we have some time, we could also, yes, all of the resources are going to be shared. Now, while we also have some time, we could also elaborate a little bit on some of the details from the beginning with regards to the methods of optimization, just to run through a quick recap. So the example for intuition that was given in the very beginning focused on a function of a single variable. So in practice, the functions that are often encountered in most applications in data science involve far more than a single variable. So for every, say, feature of your data set, you'll have some sort of parameter over which you'd want to minimize. But the premise of these algorithms, and in particular the premise of gradient descent, like always going downhill, remains the same. And so for graph theory, it is really a lot more than just about the context of cities and distances between them. I've mentioned some examples previously, but like I said, a lot of applications within data science makes very extensive use of graphs. and algorithms on graphs. So the gradient descent algorithm might often results in a solution that's not optimal. Like here, initializing it to any area but this interval, any interval but this interval, will result in a solution that's not optimal. You'll eventually get stuck in a local minimum. However, it is far more computationally cheap than simulated annealing. And so even though simulated annealing, given enough iterations and given reasonable enough cooling schedule for temperature, will yield an optimal solution. All right, in which case, this concludes the workshop. Thank you very much for attending, and I apologize for sharing the wrong window in the beginning. But I really hope that this workshop has been valuable to you, and all of the information, like I said, will be made available, so you'll have that for your reference going forward. And of course, some of the implementations that are provided by NetworkX and by this other package might be specific to the traveling salesman problem. The premise of this algorithm can really be applied in a lot of different contexts. So virtually anywhere where you're dealing with optimization, these methods are applicable. And as a main takeaway, while simulated annealing and some of these other ideas might not be very commonly used in practice, you can view them as a tool for learning. So more than anything, understanding simulated annealing and really, thinking about it is a valuable a tool because at that point, you're not really treating optimization functions as sort of a black box and really getting an insight into them because many different contexts may require slightly different optimization algorithms. But like I said, in practice, initializing a greedy algorithm to a variety of different states and minimizing over that and picking the minimum also is a very good option. So thank you very much for your time. And so that concludes our workshop. Thank you very much for attending.